I'm going to talk a bit about optimizing code for modern processors. My name is William Cohen. I have worked at Red Hat since 2000. I've mainly worked on performance monitoring tools to identify performance issues. And so I'm going to talk a bit about the kind of performance issues that you might have with modern processors now. So how many people have seen this quote? Premature optimization is the root of all evil. OK. Anyone who hasn't seen it? OK. So people interpret this sometimes as, OK, don't optimize. No. The actual more complete quote is this one here. We should forget about the small inefficiencies. Say about 97% of the time, premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. So he wasn't saying never optimize, OK? But there's a lot of times when people do dumb things in the effort to optimize, OK? Now, what we're going to talk about today is that a lot of the optimizations address specific issues with processors. If you take a look, there are specific limitations with the hardware that happen. And what we're going to do is we're going to talk about some of those today. Okay? And if you have questions, it's a small enough group that feel free to ask questions. We have a mic up here. Since this is being videotaped, they'd like to at least hear the question. So feel free to come up here and take the mic and ask the question. So this is typically the model of the process that people have in mind. Very simple, that each instruction is executed completely before moving on to the next, right? And that there's no shortcuts. If the instruction says get something from memory, the processor is supposed to get something from memory, right, to read into the processor. And vice versa, if the processor is supposed to write something in memory, it actually writes something to memory. Also, there's no guessing, like saying, hey, I think I can do this instruction early. I think I know what it's going to be. Don't do that, OK? How many people have that model in their head when they're programming? Yeah, I have that model in my head, too. I mean, pretty much, you want to keep things simple, right? And, if we take a look at, like, the original i386 processor, it had 275,000 transistors in it. And pretty much, that's the model that it pretty much used. It would go through, and if the instruction said read something from memory, it'd read something from memory, and then move on to the next one, right? That was 30 years ago or thereabouts, right? And then you take a look at 2000 Pentium 3 Coppermine. It has 21 million transistors in it. More transistors, right? And then you take a look at, more recently, 2016, the 22 processor Xeon Broadwell E5 has 7 billion transistors in it. We're talking like, what, 28,000 times more transistors? That's a lot. They're going to be doing something with that. And all these processor designers are going through and thinking, oh, OK, what are my goals when I have all these transistors? OK, first thing is correctness. It sucks when your processor doesn't compute things correctly, right? People can probably remember some examples of processor manufacturers who the floating point didn't work correctly, and that caused problems. I certainly want my bank, when they're doing computations, that the computation be correct, right? So that's the first thing, right? It's got to be correct. They're going to try to make the operations fast, right? Now, there's lots of tricks they'd use to make them fast. And what they're going to try to do is they're going to try to avoid falling back on slower mechanisms as much as possible, OK? So if you take a look at these modern processors, there's all sorts of mechanisms that are being used. So caches. Caches are really important because they avoid having to go to slow memory for accessing data. They're using pipelines so that they can process an instruction and then start another instruction right after they start processing that instruction. Branch prediction, so that when you have change in control flow, that it can keep putting things into that pipeline. Okay. Multiple execution units are needed or used often to allow you to get more work done in a given clock cycle. So rather than just having one pipeline, they may have multiple pipelines. And then a lot of the Intel processors now, you'll see the multiple logical processors on a physical processor, and that's being done so that they get better utilization of the hardware. So I remember reading that for like the Pentium 4, they did the hyperthreading, and it added about 5% hardware, and they got about 30% improvement in performance by that enhancement. And of course, every processor now seems to have actual multiple physical processors in the socket. Okay? There's lots of other mechanisms besides those. Okay? Now, this is Ellis. Question? Okay, so this is a Istopo output from my laptop I'm using here for the talk. So you see that it's a lot more than just one processor in there. Okay? You see down on the bottom, we see there's a physical core there, right? The one I just highlighted. And we see that there are 3 other cores in addition to that one. So there's, core P0, P1. Yeah, so there's 4 physical cores in this processor. And each one of those is actually 2 logical processors in there. Okay? So that's where we're using some of those transistors. And then we have our first level instruction cache, which is 32 kilobytes. And we have our level 1 data cache, which is also 32 kilobytes. And those are for different purposes. One's for instruction and one's for data. And then we have our level 2 cache, which is still, all the ones in that column are just for that core. Okay? And that's 256 kilobytes for that level 2 cache. So we have this memory hierarchy that's for that particular core. And then between all the cores, we have this level 3 cache, which is shared, and it's 6 megabytes. Okay? So that's where a lot of those transistors are going in newer processors. You'll see that they have more caches, more processors. Right? And at the very top, you'll notice it says 15 gigabytes. This is actually 16 gigabytes. I'm not sure where the 1 gigabyte went to. Okay. Now, how to optimize. Okay. You want to maximize your return on investment. Okay? And what I mean is don't guess. You'll be wrong. How many people guess and go, oh, I think I know what the problem is? Okay. And how right were you most of the time? Okay. Okay, but you guessed. Actually, you made a hypothesis probably. You said, I think it might be this. And then you made measurements to verify whether it was that or something else. Yeah. Because a lot of the processor performance, very small changes can make very dramatic changes in performance. And so by just guessing, you're probably going to get things wrong. And you really need to have some data to figure out whether some particular change is going to help. Another thing is that what you're measuring. So I know a lot of people quote like, TCP benchmarks or spec or something like that. And there is probably a lot of effort spent to get good performance out of those. However, those are particular applications which are different from your own. And so what might work for those might address a different problem than what you're seeing. So measure what you're interested in, okay? And measure things that are useful, okay? And then after you get your measurements, you're probably going to have a list of priorities saying, okay, if we fix this, this will make a big difference in our performance. This other thing, if we fix it, it's not going to make a difference, okay? So you definitely need to prioritize. And of course, address from most significant to least significant, okay? Okay, so the stupid, simple flow chart, and you probably all have this in your head too, right? You set up your environment and go, okay, set up my environment, I measure things, If my performance is good enough, performance greater than or equal to X, done. If not, I modify something and redo, okay? Yeah. I'll keep this, get your picture? Okay. Yeah. Now, there's lots of different things that could be causing performance issues. So, memory, I mean, typically if you start out like high-level view, these are the 4 that people usually think of: memory, processor, network, and storage. Okay. For this talk, I'm only going to worry about the memory and the processor, because the other ones really aren't addressed by what I'm talking about today. Okay. How many people are familiar with the Linux Perf tool? 1, 2, 3. Okay, so relatively few. Okay, so this is a tool which is built from the Linux kernel sources. It's available in Red Hat Enterprise Linux, Fedora. If you're running Debian, Linux tools is the package. So it's available on a number of different systems. It's also pretty much available for a wide variety of architectures. I just listed some, but pretty much if you're running on RHEL, it's available on all the Red Hat Enterprise Linux platforms. And what this does is it provides access to these performance monitoring events. So if you imagine the processor, some of that hardware, some of those transistors they used are now counting how many instructions did it execute, how many branches did it execute, how many cache misses did I have, how many cache accesses did I have. And this is really useful to figure out what kind of problem you have. Okay? Okay, so there's basic commands for the perf tool. If you just want like an overall count, you can use perf stat and then whatever the command is that you run normally. And what this is going to do is it's going to start up the command, it's going to take measurements on it, and then after it completes, it's going to print out some information. And I'll show you what that looks like in a moment. If you want a little bit more detail about where those events are happening, it can use a sampling mechanism. And this is using perf record, and then you pass it the command that you want to run. And it's going to record where those events are happening. Okay? And then to display that, there's the perf report. How many people use top? Okay, so there's a top-like view for perf called perf top, and I can show you that running at the end of the talk. But that kind of can give you a real-time view of what things are getting samples. Okay? And that does require root access, but it can give you some useful information at times. Okay? So let's kind of just look. So this is the output of perf stat. And this is running on a RPM build. So what it's doing is, doing the RPM build command. It's essentially building this package called systemtap. How many people use systemtap? No? Okay, not important. So what is important is that what it's doing is collecting data for that process and everything that it spawns below it. Okay? So this is an aggregate view of that run on the machine, okay, for that particular process and all the children that it spawns. Okay? And what we see at the top left is a number which is basically how many milliseconds of CPU time was used. So we see that it's 370,000 milliseconds of time. And given that number and the wall clock time, it comes up with an estimate of how many CPUs are being used on average. Okay? So over that duration of the build, it was keeping 3.1 CPUs busy on average. Okay? Now, if you think back to that Istopo diagram, how many processors were there? 8. Okay. So 3 versus 8. So there's room for improvement there. So we're not getting the full parallelism out of the machine. Okay, so that's something this is telling us. So we should take a look at what is running and figure out where the sequential parts of that build are. Okay, and so we could do better in that respect. Okay. Another number we have here is, was it 1.199 trillion cycles? So, yeah, it's a fairly substantial amount of work it's doing. So it is using that hardware monitoring to count each clock cycle each of the processors is doing. And so this gives us an idea of, you know, how much work is being done in addition to that task clock cycles, okay? And then another hardware event it's counting is the instructions, okay? So we see that we have about 853 billion instructions. So using those two numbers of cycles and instructions, we can come up with a third number, which is the average number of instructions per clock cycle, okay? So in this case, it's saying that on average, we're executing 0.7 instructions per cycle. So depending on what kind of processor it is, that may be a good or bad number, okay? In this particular case, this processor in theory can do 4 instructions in a single cycle. So there's, again, room for improvement there, okay? In this number, you would have to look it up in like the Intel optimization manual to determine how close you are to what the theoretical maximum is. It's going to vary a lot between processors. Like if you're running on like a netbook or something like that, it's only going to be able to execute, I think, 2 instructions concurrently. So that's another number to look at there. Okay. Okay. Now we want to see where it's spending its time. Okay. So if we use that perf record and then the RPM build command, what it's going to do is it's going to run. It's going to finish up the command, and then at the very end, you'll notice these 2 bottom lines, perf record woken up 113 times, and then the one that says it captured and wrote out 29 megabytes of data. So that basically is doing sampling. So how many people are familiar with what sampling is? 1, 2, okay. So a number of you are, but just to refresh memory of some people who may not be as familiar. So what it's doing is rather than recording every single event, what it's doing is every, let's say, every million cycles, it goes, okay, I want to know where the processor is at this point. And it records the instruction pointer for that sample. And so this reduces the amount of data that has to be recorded because you can't look at every single event. Okay? And we also see the number of samples there at the very end. It's, what, 496,254. So there's a number of samples recorded, and that should give us a good idea of where it's spending its time. Now, as I mentioned, it's taking a sample where the processor is. So it gets an instruction pointer. We want that to be mapped back to something that we can understand. We want to map it back to source code, right? So there's something called debug info files. And these are generated, if you use GCC, there's a -g command, and pretty much whenever we build RPMs at Red Hat, we always have the -g so that it generates that debugging information so we can do these mappings back to the source code. Now, generating that information doesn't change the performance of the code. The compiler generates the same executable code. It just has this additional information mapping the instructions in that back to the source code. And the other thing that we do is that we strip out that information. So when you install a binary RPM, it installs the executables. The debug info is in a separate debug info package, and you can install it with debug info install. So you can install that after the fact. Okay. So assuming you have the debug info installed, you can get output like this. And what we're seeing here is on the left column is the percentage of the samples. that next column is what executable those samples were in. And then the next one is which shared library, because when you load an executable, it may have shared libraries that are loaded with that executable. And that's that third column. And then the last column is the actual symbol name or the function name. Okay? And so what we see here is that on the left, the largest number of samples we have is for that first row, and it's 3.38%. So it's not a real large number. If I was using this and trying to optimize, if it's something like 20%, then I would look right at that right now. There's nothing that's like jumping out and saying, oh, this is like 10 or 20% of the time. Okay, but this is really useful in kind of like identifying where the hotspots are in your code. Okay. And we see that the first line is the C++ compiler, and which is not surprising. This package is written in C++, so it's not entirely surprising that it spends time in C++. However, the next three lines are a little bit surprising. RPM build, and then it's a compression library, and it's three functions in the compression library. So actually, that might be something to take a closer look at to see how it's actually doing the compression and seeing if there's maybe some things that can be done to improve that. Okay. If we're wanting to kind of see what's going on in the machine at this moment, we can get kind of a similar output from perf top. And so this is taken when I was doing that same RPM build, or not actually the same RPM, but the same command, a different run. And so we see kind of similar data. We see that it's spending time in the C++ compiler. We see that the HT lookup is, that function is taking time. Yeah. We don't see the compression in there because this is just a snapshot of time. So we didn't actually run it to completion and get those samples towards the end. That compression happens at the very end when it's trying to package things up. Okay. Nope. Let's see. So what I want to talk a bit about is the performance events. Okay. So different events are going to be available for different processors. Okay. So I can't tell you, okay, these are exactly the events you're going to have on that particular processor. Unfortunately, they change somewhat from processor implementation to processor implementation. Okay? And so some processors have particular events, and other ones don't have those events. But as a general rule, the first thing you're going to look at is time using cycles. That usually at least guides you what to look at first. Okay? Because if it doesn't take any time, then it's probably not a problem for what you're looking at. And then what you're going to do is you're going to use other events to find out the root cause is. Okay? And for some of this stuff, the documentation is really, you have to look at it and kind of go, okay, here's what I have available. And at the end, I have a number of pointers to documentation, which is my friend, and hopefully will be your friend at the end. Okay. So to get an idea of what's available on the machine, there's a command perf list. And this is going to give you a list of the events. And I've truncated it because there's a lot more events than these. But it gives you an idea of what is available. Okay? And so you can specify those events by the perf command, like perf stat, and then -e, like cycles, comma, instructions, will record the cycles and the instructions. Okay? In some rare cases, you may need to use raw events, but I would stay away from those. I would use the predefined names if all possible. Okay. So let's talk a bit about the processors themselves, the caches. Okay, so the main purpose of the caches is to take advantage of temporal and spatial locality, which just means simply if I access something now, I'm likely to access it a little bit later. If I access something in a certain area of memory, I'm likely to access something in that area in addition to that item. Okay? And these are small, they're not gigabytes. I mean, you saw for the L1 cache, we're talking 32 kilobytes for instruction, 32 kilobytes for data. Some processors may have a bit more, but it's still not huge. As you go up, they'll make the caches larger and slower. So what you'll see is that the caches start out being very small but very fast, and then up the hierarchy, level 2 and level 3 are going to be slower but larger. These are hardware managed, so for the most part, you don't really need to do anything for them. There's some things that the OS needs to do at times, but as a regular programmer, you're probably not going to have to do any management things. Gesundheit. Yeah. Okay, issues. So the common issues, this is a list of the common issues. Capacity misses. So again, you think about that cache being, that data cache for the first level being 32 kilobytes in size. So you only have 32 kilobytes of room. You're not going to be able to fit 128 kilobytes of stuff in 32 kilobytes. Something has to be kicked out to make room for new stuff as it's moved in. So the capacity misses, that's a fact of life, okay? And hopefully your code is structured in such a way that you don't get too many capacity misses. Conflict misses are a little bit different. So the cache is not actually full, but if you imagine, how many people are familiar with how caches work? Okay. So yeah, so the conflict misses are typically because the hardware is using a very simple hashing function to convert that address to a particular bin in the cache. And unfortunately, you end up having a lot of collisions, and so everything goes to a few of those bins in the cache, or a few of the sets in the cache. And what you want to do is you want to restructure things so that you don't have them going to that same cache line or cache set. Fault sharing. How many people are familiar with fault sharing? Oh, no one's familiar with fault sharing? Really? Oh, wait, one person. Okay. Fault sharing is a problem with multiple processors. So if you imagine a cache line has a number of bytes in it, let's say 64 bytes, right? You could probably fit a couple elements in an array in there, or a couple different data structures in there, right? It's not, the cache is not just storing 1 or 2 bytes. It's storing, let's say 64 bytes. So we have 2 elements in there. One processor using one element, another processor using another different element in there. So whenever a processor makes a modification to a cache line, it has to have the whole cache line. And so what happens is that one processor gets the cache line, makes a modification to its part of the data structure that's on half the cache line. Then the other processor wants to make a modification to the other part of the cache line that's not actually being used by the other processor. It has to gain ownership of it, and that cache line has to move to the other processor. So it can bounce back and forth between the processors. Okay. So it's not really, the processors aren't really sharing data. It's just the way that things are laid out in cache, that they end up having to move that data back and forth because of how things are grouped. Okay? And then flushes and validations. So how many people use like Java or other like just-in-time translators? Most of you do? Okay. So in those, what they're doing is they're writing code, they're generating code. They have to generate the code as data. That data is going to end up in the data cache. But if you remember the diagram that I had at the beginning with the Istopo, there's actually 2 separate caches. There's an instruction cache and a data cache. So some steps need to be taken to invalidate that data that's in the data cache and move it over to the instruction cache. So those are the kind of issues that you could have with caches. Okay. So there are some approaches to fixing these problems. For capacity misses, rather than going through like a huge array and doing one operation, let's say you have 4 steps you're doing in a very large array, and you go and you do the first step through the whole array, then do the second step through the whole array, and then do the third step through the whole array, and then do the fourth step through the whole array. Each time you do that, things are going to be flushed out of the cache, for that, and what you want to do instead maybe is break it up into smaller chunks where you do all 4 steps on a smaller region of that array, then move on to the next one. So that would be known as strip mining is the optimization term. Yeah. Okay. For the conflict misses, what you want to do is you want to change the layout. Okay. So for that, you want to avoid strides going through memory that are like powers of 2 generally. So if you have something, let's say you have an array that happens to be, like 4,000 elements long, or a 2-dimensional array that's 4,000 elements long, and then you have so many rows, that might end up with bad caching if you're going through the columns because the power of 2 accesses. Okay. For the fault sharing, what you'd want to do is you want to make sure that those 2 separate items that are unrelated end up in separate cache lines. So you want to pad out the cache line so it's large enough that it has the whole cache line to itself, and it doesn't have that other element in there that's being used by the other processor. And this can be a very significant problem with multiprocessor machines. I know that Joe Mario has talked about it in the past. Okay. For flushes and invalidations, you want to avoid mixing the data and the code, and then also avoid like doing a lot of mmap operations, because whenever you do an mmap operation, when you like map in a new region of memory or map it out, that it has to go through and do some bookkeeping to make sure things are flushed properly. Okay. So going back to the perf command. So we can look at these kinds of events using the perf commands. For the instruction cache, we can use the L1 iCache load misses, and that will give us an idea of where those misses are occurring. Okay. Similarly, we have a command for the data cache too. And then typically in Linux, they have the last level of cache is the one that's instrumented. So the L2 cache is not as much direct data for at times. So. Okay. Now, there's yet another kind of cache in the processor, and that's the translation Lookaside buffer. How many people have heard about this? Oh, everyone. Okay. Okay, so this is basically translating your virtual addresses that your program uses to actual physical addresses. And these entries, pretty much for each page, there's going to be an entry to map that virtual page to physical page. And typically the page size are 4K. You may have some processors like AR64 that are using 64 kilobyte pages. And then there's also some use of 2 megabyte pages for things, and we'll talk about that in just a moment. Typically, you'll have the TLB entries, the processor cache, anywhere from like 10 to 1,000. Okay. So like on this particular processor, there's a limited amount of memory you can touch without changing the TLB entries. So if you take a look, the first level TLB for data on this, there's 64 entries, and that each entry is 4K in size. That means that you can touch 256 kilobytes of memory without changing any of the entries. There's was that a groan there? Oh, yeah. So I'm a little bit disappointed about that too. It's like, I want to be able to use all my memory. But there's the level 2 data TLB, which has more entries. It has 512. So that means I can touch 2 megabytes of memory directly without having to change things. Some processors also do like software management TLB, but that don't really have to worry about too much. Okay. Now, some ways to help this problem is to try to group things together so that functions and data, so functions that use each other are close together, data that's associated with each other are close together so that they end up on the same page. Okay? And then one of the other optimizations that GCC can do is what's known as hot and cold code sections. So if you imagine you can indicate whether a condition is likely or unlikely. So if you take a look at the Linux kernel, they'll have actually these macros unlikely and likely. And you could borrow those definitions in your own code, and you could mark things as, yes, this is likely. Or if it's like, for example, error handler, where it's unlikely. And then what the compiler can do is it can say, oh, I'm going to arrange the code so the most likely path is the straight through path. And that code that is unlikely to run is somewhere else out of the way so that it doesn't take up space on that page. I put useful code on there rather than that code that I almost never run. Another thing that you can make use of is transparent huge pages. How many people have heard of those? Okay, one. Okay, two. Was that? Okay, yeah. So transparent huge pages are useful for like anonymous memory. And what this, for like Java and some of the other systems that use large amounts of anonymous memory, rather than having 4 kilobyte pages for that heap, it's using 2 megabyte pages. And so you have one entry mapping to 512 times the amount of memory. And so it has a lot more memory being accessible with the same number of TLB entries. Okay, for monitoring TLB, you can use ITLB load misses. This is just an example here. So I could use that to look at that. And there's a similar one for the, that's for instructions. And then for data TLB, there's a similar one. For this particular processor, it actually splits it into separate ones, one for loads and one for stores. Okay. Now, for pipelining, that all the processors are doing pipelining now. And what this does is it allows overlapping execution of the instructions. So it starts one instruction, and then the next cycle it starts another one. And so all these things are just kind of flowing through assembly line. If you imagine like auto manufacturing, right, where they have that assembly line, they're just moving the cars through and doing the various work on those. This is the same idea. There are issues with this that might happen. Like, for example, you might have an instruction that's using a result from an earlier instruction, and it has to wait for that value to be available. So hopefully the compiler can schedule it so that's less of a problem. All right. You might also have an instruction hold up the pipeline. So there are cases where, like, the instruction is doing something which pretty much changes the mode of the system or something like that, where it says, okay, I got to wait for all this to complete before I can do any more. And then lastly, you might have branches causing problems. So if you imagine that pipelining works well if you know what the next instruction is to fetch. But anytime you have a branch, or the process has a branch, it has to determine where to get the next instruction, and that can slow things down, particularly if it's a conditional branch where it may fall through it, or it may continue on to a different place. Okay. So some things that you might consider when writing your code. Avoid the slow instructions. And you're going, duh. But do you know what the slow instructions are? Okay. Well, I was going to say that one suggestion is that divide is a bad instruction. if you take a look at, how many people have heard of the Cray computer? Okay, the first Cray computer, they took a look and said, divide is hard and slow. What we're going to do is we're going to have a reciprocal instruction, and then we're just going to do everything as multiplies so they could pipeline it. Now, there are some numerical issues with that, in terms of numerical analysis, but the performance was a big enough improvement that they said, we're not going to do divide. We're just going to have this reciprocal instruction. And then we're just going to do multiplies for things. So in general, if you can avoid divides, that's a good thing. There are other instructions besides divides, but that's one that's probably most commonly going to be seen in code. You can look at the optimization manuals for ARM and Intel and stuff like that, and they'll list out saying how many cycles these instructions take, and they'll point out other things like that. Okay. Another thing you can do is unroll loops. So if you imagine you have a loop that does a memory copy, right? You would just say copy 1 byte, am I done, and just keep looping. If you take a look at virtually all the memory copies on the system, what they're doing is they unroll their loop so that they're doing maybe 64 copies at an iteration. They'll have some cleanup code at the beginning and the end, but they'll go through and the main body of the loop, they'll do, let's say 64 iterations or maybe 16 iterations at a time. And the advantage of that is that you have this larger group of instructions you can schedule, or the compiler can schedule. And it's much easier for the compiler to schedule that large group of instructions than a small group. So if you imagine, it can go through and interleave those instructions also. So it can do a better job of trying to say, okay, this instruction is dependent on this instruction, so I'm going to put these other things that are unrelated and get better performance. And then also it has fewer branches, which also can help performance. Okay, so branch prediction. This is really important on all the modern processors. What it's doing is it's figuring out what the next instruction is to feed to the processor. And particularly for conditional branches, it's going to try to predict which way it should be going. If it gets it right, it's great, because then that means it said it speculatively executed code and it was successful in executing that code. There are issues sometimes that it could get the prediction wrong. And if it gets the prediction wrong, it basically has to make it seem like, oh, I didn't do that work, and it wastes it. Okay? And this can take a little while to clear out. So if you imagine you have that pipeline, it has all those things going through the pipeline. It says, whoa, 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 I need to get rid of those. And so pretty much it has to start anew. And so all that stuff that was in the pipeline has to be thrown away. And so it can take on the order of 10 cycles or 20 cycles to kind of get rid of that wasted work. So things that can be done. The loop unrolling, that'll help with this because you have fewer branches. The hints, to say likelihood of the conditional can help too. So for example, if you have error handling code, you could mark that as this is unlikely to be used. And then that will help the compiler do the right thing in terms of code generation. Another thing that you can have is unpredictable branches. So for example, absolute value is typically done by, is this value less than 0? If it's less than 0, change the sign. Okay? But usually that's being used for something that the data doesn't really have much rhyme or reason, and so the predictor gets that wrong a lot. And so there are ways of recoding that so it's just straight line code, so it's doing a bit manipulation instead. Okay. So there are some events. There's branches and branches misses that allow you to kind of see how well or poorly the hardware is doing. And actually, if you remember on the perf stat, it actually printed out that information. Okay, so I know that you guys are not going to be able to, oh, okay, this is everything I need to know. So instead, what I do is at the end, I have pointers to various things that might be helpful. So there's perf, if you type in perf help, it'll print out information. Also, you can do man perf, and then there's other things on there. Vince Weaver also has a website that describes perf in more details. Uli Drepper has a really good write-up about what every programmer should know about memory. And it goes into a great amount of detail about how caches work, how various memory hardware works. And so it gives you a very good, complete understanding of how that works. And given the cost of memory accesses, it's a really good thing to read. For general performance tuning, Brendan Gregg has some good material on his website. So he does a lot of work for Netflix and performance tuning. So it's good to look to see how he does things. For actual hardware you're using, I just have a couple examples up here for AMD and for Intel. So they have code optimization guides, which describe what things you could do for their particular processors. Okay. And of course, you're already here at the summit and DevNation. So there are some other talks that you might be interested in. If you're interested in Java, you might want to go to the DevNation talk tomorrow, talking about thermostat. There's also performance, I guess Shaq is giving his talk about performance analysis. And then after that, we have a performance bird of feather. This is the last two are Thursday, afternoon, early evening. So there'll be a number of people that work on performance tools at Red Hat at the performance BOF. So, yeah. So, and then pretty much, I can go through and demonstrate some of the stuff and answer questions. So, okay. Actually, I guess we got a microphone here, so if. Yep.
For high-level languages like Java, how do you actually map to those low-level constructs?
Oh, that's an excellent question. So there is, yeah, I guess you can just leave the microphone there. So there's perf map agent, which some people at Red Hat have used to allow you to take the data that you're collecting and map it back to the methods. So you could use something, as I said, like perf map agent, and that stuff is they're working incorporating that into perf, but it's not currently in Red Hat Enterprise Linux. But that's something that you could look at to use to get that information. And what it's basically doing is it's using that mechanism that Java has, a JVM TI mechanism that records where methods are located after they're compiled. Yeah. Okay. You had a question?
Hi. I remember a few slides back you said something about hinting to the compiler, or how exactly do you hint stuff to the compiler?
Okay. Okay.
Like, are there code examples?
Okay. Okay. So let's see. That I actually have a blog entry on the developer Red Hat developer blog. So let me see if I can find that real quick, and that will actually, yeah. So like right here, this is from the Linux kernel, but you can see that, yeah. Yeah. So this would be an example. Let me just go back and see if I can find the actual definitions here. Let's see. Yeah. So this is actual. Yeah. So these are exactly what you're looking for. So you could have those kind of things in your own code, and then you can mark your own code as likely or unlikely for those things. The compiler does try to figure out, for like how the probability of certain branches, but for other ones, it can't really tell because you're passing in a parameter or doing some other check where it's not obvious. Yeah, yeah. But if you look through the kernel code, they use this quite a bit. Yeah, and this has a benefit of it can move things to like off to a separate page, but then also it will go through and try to make it so it's more linear, because that's the best kind of code for the processor, if it just can kind of go through sequentially and not have to jump around to random places. Yeah. Okay. Okay. Any other questions? No? Well, thank you very much.